Welcome back to another HVAC-Engineering-Techie training video. Today we're going to be talking about HVAC air handlers and fan coil systems. This is part of our system courses, or S number courses. This is S number 7. And this is designed to talk to you about air handlers and fan coils, how they're made, what they contain, what they're supposed to do. And so everything you need to know about an air handler we'll cover today. So remember this channel. Talk about engineering, we talk about construction equipment, systems, tab, test and balance, controls, efficiency and performance, all other things about HVAC systems that you need to know as an educational service. So hopefully this is helpful to you to learn a little bit more about air handlers if you haven't been in the industry a long time. So before we start, I'd like you to become a subscriber. Please become a member of our technical community that learning and trying to learn more about HVAC and what's important about HVAC. So let's go ahead and do that. Let's get started. All righty. Well, welcome to air handler operations. We're going to talk a little bit about air handlers. One thing to know about air handlers is that they're the heart of an HVAC system, be able to transfer the heat from the space up to the coil to be able to change the temperature of the air to keep us all comfortable. So this is a typical room, just a room, and of course it has an air handler up here of some kind that can be mounted inside the space or outside the space on the roof. Basically, it has a return duct that sucks the air from the space across the filter, across the coil. The fan catches the air and pushes it out to a distribution system. And then it goes to a ceiling diffuser or some kind of diffuser somewhere, maybe a sidewall even, and it discharges the air into space. Now, grills and registers are designed to be able to take the air and have it and hug the ceiling. There's that by quanta effect, where the air actually kind of hugs the ceiling, and as it gets slow enough velocity, it begins to drop out. So the engineers designed these grills to be in the space so that they will always cool the whole space. And returns can be sidewall, down low, up high, can be in the ceiling, anywhere. And then the other thing here is a fresh air inlet. And because the fan is sucking the air this way and blowing the air this way, this is all under negative pressure. So if you put a damper here to the outside, it will suck outside air in. So as a balance contractor, it's important for us to set up outside air so that this space is slightly under slightly positive pressure. And the reason for that is all buildings leak air. It's impossible to build a totally tight building. So we want to produce enough outside air to cover up those leaks. So this is positive pressure. And the reason we do that is because if you don't do that, the air comes in, it'd be negative pressure, and it brings dirt, debris, fumes, all kinds of things with it. And it makes the space harder to air conditioning because wherever it's leaking, now that space is at a different temperature or different humidity. So we don't want this negative. We want at least neutral, but normally prefer about 0.02 inches of water column. So that's how basically air handlers operate. Now the thing is important to realize about an air handler, they're all custom built. Now they have certain models, but they'll come with a different size coil if you need it. Come with more than one coil, maybe a heating coil, cooling coil, maybe a preheating coil, and a cooling coil, and a heating coil. I mean, all kinds of things in here can be put in, and we'll go over that. So here's all the thing I just told you. So that it goes around. I always forget that I have these things printed out there. All right, so now we're going to talk about components. You can see inside the unit there's all kinds of components. There's fans, coils, filters, many things we're going to go over. And they're all different, so you can get different types to meet different applications. So when you order an air handler, you're basically ordering a custom unit, except maybe for fan coil unit. You might be able to get a standard fan coil unit that maybe has more capacity than you actually need, but that's what's available. But even those, most of those are also custom. So there's fans, cooling coils, there's heating coils, there's DX coils, which is for refrigerant coils, condensing units. In case you got a DX coil, you got to have a condensing unit go with it. Ultraviolet disinfectant lamps, we use those in units. We'll talk about where those go and what they are. Different kinds of filters, different capacity filters, different filter ratings. Dampers, different kinds of dampers within the unit. You can have isolation dampers on the discharge and suction side. You have fresh air dampers, lots of different dampers. Heat exchangers, we can have heat exchangers inside of it. We'll go over that. You can have gas furnace for heating. Have humidifiers to add moisture to the air. Have air washers, which we'll go over what that is. And you can have condensate drains, which are actually really, really important. And we'll spend a few minutes talking about those also. So let's start talking about fans. All right, so there's different kinds of fans. They're made differently. The first kind we'll talk about is a forward curve. And forward curve is exactly like the name says. The blades are actually little forward curve that catch the air. As this turns, it catches the air and throws the air off, and it throws it against the volute, and that's how it pressurizes. Fans are also made in what we call single inlet or double inlet, and that just means that if it's a double inlet, the wheel can suck air from both ways. If it's a single inlet, then the backside will be solid. They can only suck air from one side. So this happens to be, shows you it's a double inlet wheel. Now, forward curve wheels have some particular application, and normally it's for low pressure, higher air. They're higher RPM, and this is what you would have on your residential unit in your house. Commercial, we get much different wheels. So low pressure. We have next one is backward incline. Now, backward incline, you'll see the wheel. It turns in this direction, and you can see these wheels are slanted backwards, back, and they actually paddle the air like you're paddling, and that's what that backward wheel is done. The only problem with these are they're very good fan, and majority of your commercial fans will be backward inclined. And the problem is most people look at this and say it's running backwards. They want it to run this way. And it'll push air that way, but not very much. It'll push maybe 10, 15% of its airflow when it's running backwards. But that's something you have to check, because most, including operators, will look at a fan and say, well, that's running backwards. But it's not. It runs pushing. It's paddling that air as it goes by. And these can be low to high pressure fans. And then we have airfoils, and airfoils are the same as a backward inclined, except that the blade itself is like an airplane wing. It's an airfoil. And here what happens is these have slightly less turbulence, and they also do it backwards, just like a backward incline, except they're airfoil blades. And they do have slightly medium to high pressure again. They're slightly more efficient than a backward incline. However, they're a lot more expensive, so we only see those in real special applications or applications that are large fans. We have what's called a plug fan. A plug fan is designed to sit in a plenum space. And what you do is this would be the plenum right here. And you install these, and they will suck the air in through the plenum wall and pressurize the plenum. Okay, so we have this thing called system effect. And system effect is caused when you take a fan and you suck air into the wheel, and then you push it out of the wheel, and the air is turning. What happens is it's turning this way, and if it goes out and goes this way, it's no problem. But if you make the air come out of the fan and it's twirling this way, you want it to go this way, it means the air has to stop twirling and start going this way. So it actually stops this twirl and it changes the velocity pressure to zero, and then it has to increase the velocity from zero back up to what it needs to be to go down the duct. And it's called system effect. Now, plug fans do not have system effect because they've already taken it. Now, they advertise they have no system effect, and so in this plenum, you can take air out any way you want, because it doesn't matter, because this plenum is just a pressure plenum. But that speeding the air back up to get out of that duct connection, that's system effect. So basically, these have already taken the effect. So basically, they're not as efficient as a regular fan because they've got that effect in here. And these are what you call arrays. So this is low pressure to medium pressure fans, and this is a fan array where you'll have 3 to 20 fans all housed like this. These are the suctions, pressurizes the plenum, And the air can keep going this way, or it can go any way it wants to. But this is the process for a plug fan. The plug fans are basically backward inclined blades, but they're good fans. You see them everywhere now. The reason because of their popularity is because of one, cost, and two is this is not a very big dimension. If you had 6 fans here, you need to have one centrifugal. This distance would be way out here. So these are space savings, which can be important to people. We have what's called vane axial, and these are basically like jet engines, vane axial air, and they suck the air whichever direction it's supposed to go. And these are high pressure fans, capable of high pressure. They're also capable of low pressure, but they're kind of expensive for low pressure. So most pressure people use them for high pressure applications. All right, let's look at cooling coils. Well, cooling coils or heating coils, but we'll talk about heating coils separate, basically have fins on tubes, and the fins are there to give surface area for the air to change its temperature. Have different rows. They can come from 1 to 10 rows. Now remember, as this is a row, this is a row, that's a row, that's a row. So we count the rows that way. And what the difference is a 2-row coil or 1-row coil has very little pressure drop, air pressure drop, and so it doesn't move a lot of heat. But a 10-row coil moves a lot of heat. But the problem is it's hard to clean a 10-row coil. There's a whole bunch of them there. So most cooling coils are 6 to 8 row. Most heating coils are 2 to 4 row. And that's a reasonable number of heat. Now, they also have spacing of these fins. It's called FBI, fins per inch. And that's something that you have to be careful of, because if you have 24 fins per inch, it moves more heat. The coil moves more heat than if you have 10 fins per inch, because there's more surface area on the coil. The problem is anything under 10 or 12 fins per inch, very difficult to clean. And a 24 fin coil is almost impossible to clean. So when I was doing commissioning, I would almost never allow anything over 12 fin. And that's because if you make it very difficult to clean, the operators will never clean them, and then they'll get impacted and they'll have to be changed. So we don't do that. 4 to 10 row, 8, 24 fin. But like I said, just because you can doesn't mean you should. Counterflow. Now, chill water means counterflow means that we have the air come in this direction and we have the water go in this direction. So basically, we want the coldest water coming in at the leaving side of the coil. If you don't do that, if you pipe it so the coldest coil is coming to the entering side, what happens is the air is entering warm, and as it hits this cold coil, it starts to cool down the air, and it leaves down here. The problem is this is not the coldest water. This is return water temperature. So this will be up here slightly, and that what happens is it makes it this doesn't dehumidify. But you want the coldest water here. So if you have the coldest water coming in here, it drops it. The air leaving is almost just a few degrees higher than the actual water temperature, and it will actually dehumidify more. So that's really important in chill water coils. I always told my people that just make sure all coils are counterflow, then you'll never make a mistake. Counterflow. So critical to coil performance. They have multiple coils. You can have stacked coils. You have coils end to end. So this means that you got too much. You have a big air handler. And it's, if you have an air handler that's 8 foot high, an 8 foot by 16 foot coil's a monster. And it's hard to deal with. So they would have multiple coils in that arrangement. And a cooling coil would have multiple pans for that arrangement. So you wouldn't want this cooling coil condensate flowing down this coil. So you would want them to have their own pans. You can have series coils that they go. Now, why would you have a series coil? Well, if you had an industrial process or something where you had a huge delta T, more than a 10-row coil or an 8-row coil would handle, so you put 2 coils in series. It's not really impossible to do, but you can do that. Heating coils are the same as cooling coils. 1 to 6 row normally. 8 to 24 fins, again, it should never be 24. It should be something less than 12. You can have electric coils. You can have electric heaters in an air handler. They can be stage coils, 1 through 8 stages. We don't normally have more than 8 stages because that's getting pretty complicated as it is. The only thing that's important about electric coils is air velocity. You can't have dead spots in this coil because this is a standard coil, and you notice that these heating elements are exposed. So if you have an area that has no flow, those coils will heat up, get too hot, and burn out. So you have to have velocity across this coil. And then right here is a thermal element that watches that. If it gets too hot, it shuts off the heater. So many times I've had to come in and build baffles in here to push more air across this coil or to certain areas of the coil because it was too hot of air. So that is one problem. 1 to 5 kW coils, that's just a practical limitations of the amount of power going into it. And that's one reason why we stage a coil. Stage it to keep the kW smaller in the coils. Or SCR, silicon control rectifier, which means it can be modulating control, it can be 0 to 100% or anywhere in between. Stage coils, of course, are off or on. Electric heating elements. That one before I showed you, this one here is a standard open coil. So the heating element's open to the air. This is a coil cowl rod heater where it's the actual wire element is encased in another element. So this is a tube. And what it means here is this one's much less susceptible to that velocity problem, or if you have contaminated air. So this coil here, if you have lint, it'll burn it. If you have paper in it, it'll catch it on fire. So you have to be careful because these get red hot. So you can't have contaminated air here. I mean, you can have dust in it, stuff like that, but if you have paper fines blowing down it, you have a problem. You get smoke, so you don't want that. These units won't do that. These units are basically different kinds of wire elements. Cowl rod heater. The cowl rod heater lasts a lot longer. Doesn't produce as much heat as an open element, but they do last a lot longer. So refrigeration coils, DX coils. Now, DX coils are made differently in that they have rows just like the other one, but here we have a distributor tube that actually breaks up the refrigerant and puts in every single row element. So basically, as a row goes, this element feeds here and feeds out here. Might go through there several times. That's our distributor. Other than that, it's the same thing, 1 to 6 row normally, 8 to 24 fin per inch. You can get an 8 row one, but basically that normally is a double stage coil, but you can. You can get a vertical A coil. This is like a residential unit, and this has a coil up like this. And the only thing that makes this kind of unique is the way it handles a condensate. It's got a little bit of trough bands down here to catch a condensate that goes down the coil. Multiple stages. You can have a single stage coil. So you can have phase control. Phase control stage coils have one little issue, and that is if you have one unit on, it needs to be the top one. Because why that is because if this one's off and this one's on, this one is removing water, and the water will drain down and wet this coil so they have the same airflow. If this one's dry and this one's wet, or let's say this one's wet and this one's dry, this one will have less air resistance, so it'll have more airflow. It's not significant, but it means that now you thought you were doing 50% capacity, maybe you only have 40% of the airflow. So that is why we always we want them both wet if we can do that. Or we can have row control, which basically means we can turn on 6 rows and then we can turn on 6 rows, and they're both independent, but this way we get a whole bunch of capacity. And this is used if we have so much capacity that one coil won't do it. And then we can have intertwine. Now, there's been a lot of discussion. What is best? Phase control, row control, or intertwine coil? Now, what an intertwine coil means is that it's got 2 stages here, and this one feeds one, and then this one feeds one. So no matter what stage you have an entire cold coil. It has 2 circuits, but it's got them intertwined amongst the whole coil. And my opinion is that intertwined is absolutely the best if you got a multi-stage. And I was part of a group that wrote a tech standard rule of thumbs for balance guys. It was a big book. It took us a year or 2 to do it. And I didn't know the answer to this question, so I reached out to all the major manufacturers, and the answers astounded me. We had some that said phase control, we had some that said row control, we had some that said intertwined. So I thought, well, that's really weird. So I went back and looked, and what they did is they told me what they make. So there were some manufacturers that made phase control. That's what they said was best. They were row control. They said that was best. And then intertwined, intertwine's the best. So They didn't really answer the question. They just told me what they sell. So that one wasn't beneficial. Condensing units, of course, get small capacity units, 1 to 5 ton. You get large capacity, you can go to 15 ton or so. You can get bigger ones, but normally for a single coil, there's not bigger ones. You get to 120 ton, I guess. Okay, UVC lamps. They're downstream of the cooling coil. So what we do is we put these lamps so that they shine on the downstream side of the coil. And what they do is this ultraviolet kills any bacteria that might get on that coil, which actually keeps the coil clean. So that's what they're for, is to keep these coils clean. They will disinfect. Now, during COVID, we researched a lot to see if these coils could be used to kill the bacteria. And they will, but the problem was there's not enough dwell time here. You would have to have several sets, and the dwell time needs to be 10 or 15 seconds, which that ain't working here. This air is moving down the road. So they do keep a coil clean, and they're very good. They pay for themselves in energy just by keeping a coil clean. Because a cooling coil, as it fouls, just a few microns of dust or dirt or bacteria on a coil reduces by 10%. So it's very significant. And so these basically helps keep mold and bacteria from growing on the coil or in the drain pan also. So it helps. Basically, it keeps the coil clean and requires less cleaning. Improved energy efficiency of the coil for heat transfer. Many may not kill viruses due to limited dwell time, like I talked about. Oh, there is only one other problem here. Is these UVC lamps, which means that's the C basically telling you that it's a light that will kill a bacteria. But remember, you made up a bacteria, so they will hurt you. So the units has to be installed so that if anyone opens an access door, these go off. You can't have these on. It'll number one, it'll blind you. Number two, it will actually give you a serious sunburn. So you don't want to be in a space and have those shining on you. Filters. We have pre-filters. They can be 1, 2, or 4 inch. It can be MERV 4-8. Now, MERV is a rating for filters. It was a rating trying to make sure everyone understood what's a good filter, what's not. So this is a dust stop filter like you might have at home. They're about too good to 35%. Catch lint stuff. Don't catch much else, but that's what they do. You have pleated filters. Pleated filters are pleated to get a lot more area, surface area in there. Then you have final filters. They can be pleated filters, MERV 8 to 16. Cartridge filters, MERV 12 to 16. It's getting up there. These cartridge filters come in 4, 6, 8, and 12 inch deep. And then bag filters are MERV 12 to 16. And bag filters are normally like 24 to 36 inches deep. And of course, the air is flowing this direction in the bag. And they have these, the bag catches the material. Then we have special filters. We have HEPA filters, which are used for medical situation or any place we can't have any dust. Clean rooms basically use it, any special manufacturing. And then MERV 17 to 20. The difference, of course, you realize as we go down the list, price goes up, right? So, and also these have a high pressure drop. So when you use these, you have to have fans for them to get through them. They're normally 12 inches deep. This is a standard 24 by 24 by 12 inches deep. They also come 24 by 48 inches, 4 inches deep. So there's different sizes of these filters. And you can absorb it. Now, absorbent filters are special filters that have these compartments in them filled with some kind of material that will absorb what you want absorbed out of the air. And so you can buy these with charcoal to get fumes and odors out. You can get them with special. I've used these for SO2 reduction of SO2 in the airstream, which makes sulfuric acid. So but the only problem with these is you have to regenerate this material ever so often. So you don't change a filter, but what you do is you pull them out, empty the old stuff out of this and put new in, and close them back up and put them back in. These are expensive, of course, but they do work. So you can take jet fuel out of the air, you can take odors out of the air, you can take different gases depending on what absorbent they have. So that's basically the filter systems. Here's the MERV rating. It tells you what it's for. So these blue are all the HEPA lines. These are all the higher ranges. And basically nowadays, if you want a really good filter, you need to be at a MERV 13 to 16. That will take a virus out of the airstream. Anything below will not. Anything above about 8 will start taking out fumes and vapors like smoke. Will take it out of the air. So there's different things to do there. So you can read this chart. Will tell you exactly what size of filter thickness and what MERV rating and what the pressure drops are for. So that's filters. Dampers. Okay, we can get isolation dampers. Shut the unit off, especially for fire dampers. It can be fire or not. We get OBDs, or opposed blade damper. And the OBDs have blades in here that oppose each other. And they shut off fairly positive. Now, all the dampers we have in air systems, we have what's called low leak dampers. We have ultra low leak dampers, and we have standard dampers. Standard dampers leak quite a bit. I mean, so they're leaking somewhere around 3 to 5% of air. An ultra low leak still leaks 1.5% or so. Ultra, maybe 1% or below, but they're never seal tight. Just can't be. We have parallel blade, which basically, so this one here, you notice that the blades are opposite each other, and this area gets smaller and smaller and smaller until it closes. This one here is parallel, so they just all close together. And the difference between the two is an opposed blade creates a jet of air, and a parallel blade creates a air pattern direction. So you can use a parallel blade damper to mix air. You can't of an OBD. OBDs are much more popular, a little more positive flows, but they also can't mix air with them. With this one here, you can have the outside air damper point towards the return air damper, so it mixes better. But either one, and there's no other value that makes them better than the other. I've really spent a lot of time trying to figure this out. That they both do the same job, but OBD is the one that's normal, and parallel is normal used on an air handler mixing plate. Economizer dampers. This is an economizer section, and what this does basically is it allows you to bring in 100% outside air to use for cooling of the system during colder months. So what happens here, the return air comes in here, the relief air is here, this is a return damper, and the outside air comes in here. So what happens is the supply fan is over here sucking air this way. This here is under negative pressure because we have this damper closed. If we're in economizer mode, this damper's closed. So all the air coming in here has a fan that blows it all out in relief air, and the air handler, the supply fan, sucks in all the air out of the outside. Now there's different configurations of how to do this fan, but the reason we have a return fan is so this doesn't affect room pressure. If you don't have a fan here, now the supply fan has to pressurize the space to be able to blow it through here. Now these are on economizers that would always blow the doors open, right? So you take the supply fan to suck in 100% outside air, pressurize the space, blows the outside air doors open, and to get the air out of here. So you either need an exhaust fan, a fan up here, or a return fan to make sure the space is the same. And this is a duct section to an air handling unit where the return air comes up here. It's either exhausted out here, it goes in here, and this is the outside air damper. Face and bypass dampers for coil bypass. You could have heat wheel bypass, where when this is not being used, they open it up around it, or they can have a face damper to force the air around it. Those are all special applications, but they do come inside the air handlers. Heat exchangers. You can get an air-to-air heat exchanger, the dry bulb type. You can get enthalpy type that actually move moisture between them. And these are designed for systems that have a large outside air load. So you can take the outside air and put it through here, and then put the exhaust air through here, or relief air through here. And you can capture the heat of the relief air or the exhaust air to put it in the incoming air. You can have heat wheel exchangers, which exchange air that way. The difference between a heat exchanger like this and a heat exchanger like this is the amount of bypass. And the heat wheels come in dry bulb or enthalpy bulb. But what happens is this is the one side and this is one side. So this is probably the This is probably the exhaust air. This is the outside air coming in. So you can see that they're opposite. This way, so this one goes this way. Well, the only thing that separates these two streams, is there's brushes right here and brushes around the wheel. And this wheel is made of a metal fabric. With sometimes it's impinged with ingredients to help it capture moisture. But so these do leak. These do leak between each other. So if you have a contaminated airstream you're exhausting, you cannot use these because they will allow the contaminant on the other side. The other thing is really important that these be reverse flow. If you have both these flow in the same direction, then what happens is wheel gets impacted with debris. This way, this air will blow it off. If this has debris in it, like lint, and it sticks to the wheel, this will blow it off. If you don't do that, have the same way, this wheel doesn't last long before it gets clogged up. Wheel type issues, like I said, if they do that also, if this is coated with a desiccant to make it move moisture, and you let it get soaked for too long, the desiccant has to be cleaned, and the only way it's cleaned is with heat. So normally you have to remove them, heat them up in a furnace or in an oven or something to throw off the heat. Or sometimes we would bring in heaters, have heating on this side so the heat would blow off the moisture. Either way, the enthalpy wheels can get saturated. It can be a problem. Bypass air between streams. So now this one here, that other heat exchanger, it's tightly sealed between them. It never transfers air between them, and that one can be used on contaminated air. This one should not be. Runaround coils, this one can be used on contaminated air, which basically has a coil in the cold stream, one in the hot stream, and one can be exhaust, one can be inlet. And it has a water stream flowing between them, and it transfers heat that way. Now, this one doesn't transfer as much heat as the other one, the heat wheel, but it does transfer heat. It's a runaround coil. This is really popular for very large airflows. For like labs that have 100% outside air, these can move quite a bit of heat. They're only about 70% effective, but still 70%, so you can move a lot of heat around that. It's dry bulb only, can never move wet bulb. And then we have a heat pipe exchanger. And heat pipes kind of fallen out of favor, but basically what happens is they have a tube inside of them that, let's get to it here. It's a tube, a closed tube that has a wick, and it has a certain amount of refrigerant in it. And as you tilt it one direction, you can, this here is the evaporation, and this is the condensation up here. So you've flown it so the refrigerant drains back to the evaporator side, and then the heat causes it to evaporate, and it flows back, and it just keeps doing this. And the only thing that's really unique about these is you have to tilt the coil between summer and winter. So basically this is on a tilt mechanism, and winter it will tilt the coil this way, and summer it'll tilt it that way. But these are good for, there's no contamination between them, so you can do them separate. There's no water, no fluid, and they're just refrigerant built inside the tube. Gas furnace. A gas furnace section can be single stage, multi-stage, can be modulating, and built inside the air handling unit. You can have gas furnaces on the outside of the air handling unit. One thing that's interesting about these is supply duct mounted, single stage and multi-stage, and modulating, same, and multiple units in series. So if you have a job that's really in cold country, like Alaska or somewhere, Antarctica, you can put 2 or 3 of these in series. Or if you got an industrial process where you need really warm air, like if you need 150 degree air, you can put 2 of them in series or 3 of them in series and do it that way. So these are advantageous to do that. Humidifiers, you get steam humidifiers, which is the gold standard, of course, which is takes live steam and distributes it throughout the ductwork. This is a module of ductwork. It has a valve that turns it on and off, modulating, so you can put a varying amount in there. The only problem with these is they need clean steam to be in the airstream. If you put regular steam that's been treated with amines and all these other chemicals, into the airstream, you could cause indoor air quality issues. So we don't do that. Duct mounted, clean steam, like I said. Direct space mounted, you could get these in direct space that have a fan built on them. You could canister type. Now this is a package unit answer to steam heat. You don't need a boiler. You just hook these up. These have a canister in here with cowl rods in them, and the electricity causes the water to turn to steam, and then this have a hose go up to a steam accumulator in the unit. These are good conducted space, so water cannot be DI water. So one of the problems here is that if you have water that's high in scale, high in calcium and magnesium, this will plate it out because it's boiling it, and this is all pure steam going out here. And so these will not last so long. The problem is they're expensive. It's $400 to $600 a piece. So I had a client hire me at a big data center, and they were losing them every 3 months, and they had like 10 of them. I said, what can you do? So I said, well, we can run RO water through them. So we'll put an RO water on the incoming water of these units and clean them. Well, they didn't work at all because there was not enough solids in the water to produce the conductance and electricity from the rods in here. So we went back, and I put a TDS controller on it, and I had it run at about 50 TDS. So I mixed the dirty water with the RO water, and we made these last for 2 or 3 years producing steam. So it was a big win for them to do that. Canisters replace periodically due to scale, and if you put cleaner water in them, you have less scale. Electric steam generators, cowl rod pan heater. So what happens, this has a cowl rod in this, has a pan with a float valve, and it keeps the water level right here. And this cowl rod gets hot and burns, turns it to steam, and steam goes out here. These are duct mounted. So the top is open, so it peels it. Now, these work fine, and they're found a lot of times in computer room units and things like that. We have a quartz lamp one, which is exactly the same, except it has a quartz lamp and a shield, and it heats the surface of the water, same thing. The problem with these two, though, is scale. The scale causes these to scale up, and boy, they have huge maintenance problems to take care of. So both these are not too popular, to tell you the truth. Canister is what normally happens, but because these are such maintenance issues to deal with it. Atomizing nozzle, which is just a fine nozzle, have to have real high pressure water, normally 300 to 600 psi water. It has a special pump, of course, to do that, and it breaks the water into real fine mist. And we use these in my town to cool patios and things. The problem is, though, is that to talk about it, these should not have calcium in the water. If they do, this thing is so powerful that it breaks the calcium into the smallest final particles and can cause breathing issues. So this is a problem. If you got high calcium, magnesium water, you need to clean the water. Now, this pure water RO would work perfect for these. Otherwise, these are going to put out that mist. And then anything these spray on, if they got calcium and magnesium, it turns out to be white. It will paint it with that stuff. You realize what's going on in your lungs. Pad evaporation, this is a normal residential humidifier where it's got a pan on the side of the duct or on the bottom of the duct, and it fills this container full of water, and it's got this metal screen in here that wicks the water up, and as the air goes across it, it evaporates into the airstream, humidifying the air. Only problem with these is the air needs to be warm. This is cold air, won't evaporate into it, so that's the only problem. This air needs to be significantly warmer than the water. Air washers. Now, an air washer is basically an evap cooler. It takes a pump, has a basin down here of water, and it sprays it on this media. And as air goes through it, the air evaporates the moisture into the air, humidifying it. Now, these work fine, except they are maintenance intensive, and they're used on air handlers to humidify a large quantity of air. Because all the other humidifiers we mentioned are fairly energy hogs of adding humidity. This is a very low energy hog. It's a high maintenance issue. There's no free lunch. And that's called an air washer. It's really an evap cooler section, but it's called an air washer. water circulation pump, lower air temperature via water. That is another problem. Normally we have these in higher atmospheres where we have low dry, high desert condition. We have low humidity, and if you're high altitude, these things work too good. So I've seen these drop the air 20 degrees in about 15 seconds. So that's a lot. So what happens is the space gets confused because it makes it way too cold, and these are hard to modulate. They're really an off-on device, and by off-on I mean full-on and off. So it's hard to humidify with these if you have a really high altitude dry situation. These can work too well. Adds humidity to the air. Okay, now condensate drains. And most people say, well, what's that big deal about a condensate drain? Just let it drain the water out of the air handler. Well, the condensate drain is responsible for keeping the air in the air handler separate from the condensate outside the unit. It needs to get, we don't want the condensate staying inside the unit. Let the condensate stay inside the pan. It can grow mold and all kinds of stuff in here. And secondly, we need to protect it. Now, there's two kinds of coils. A draw-through configuration prevents the air from being sucked into the unit. So this is a draw-through, so this is under negative pressure. If you don't have a condensate drain, it will be sucking air in from this condensate drain into this unit. Well, what happens, this airflow coming in here causes little waves. And when this water waves up, any solids tend to fall out. So eventually, over time, this thing builds a dam around the condensate drain. So what we have now is we have a big puddle of water in the condensate drain pan, and we end up with all the AHU issues in this pan. It has to be clean. Now, some engineers design condensate traps all kinds of ways, which is unfortunate because condensate traps are designed from physics, not from any designer's intentions. So if you don't design them like this shows, they're probably not going to work. So what happens is this has to be low enough, this trap has to be low enough and deep enough so that the pressure in here can't suck the water right into the unit. So that has to be deeper. So these dimensions are 1 greater than the negative static pressure of the unit. So you have to kind of know what static pressure is going to be in here before you can design one. And then some designers say we don't need a vent up here. We're going to close that off. We're not going to have one because the water will drain out of the unit. Well, it will, as long as the amount of water is not enough to fully fill the pipe. If you fill up the pipe, this will become vapor locked. So basically, this has to, without this vent here, this has to be the vent. So it has to be running probably less than a quarter full. So it needs to be a big condensate drain for that to work. Normally this vent is here to vent this drain, not to vent the trap, to vent the drain. So a lot of people this way and put a solid cap on here. Totally defeats its purpose. Have no idea what's on their mind. Say, well, we don't want things to be able to get down there. Well, fine. And put a screen on it or a vented cap. It's got to have a vent. It can't be plugged or solid. And then you have positive pressure. These are blow-through units. This is positive pressure. So the trap still looks the same, but all these dimensions change. Because now we don't want this pushing the water out of the trap. Because once there's no water in the trap, then it's no use. It's not a trap anymore. And I know if you guys have ever bought a package unit and the factory ships you a little bent piece of plastic, totally worthless. It's not going to do anything. It'd be just as good to not have anything of that. So traps are so simple, but still, as a commissioner, they were wrong on every job. It was amazing. This is the dam I talked about. This is what happens when you get it. The dam builds up in the water, can't get out of there because this is here. You have to clean the pan. And that's the condensate flowing half full. Nor they need to be less. It needs to be enough here to be the continuous vent. And what a lot of people don't think about it is that seems logical until you put an elbow and turn it down, go down a wall or something. Now all bets are off because that pipe may fill with water because it's falling down. So you have to have enough area so that when the water flows around the pipe, it doesn't close to close it off. So condensate traps are really important. I have seen jobs that have millions of dollars in damages because of one condensate drain. So you know what I mean, is they backed up, caused growth, caused IAQ problems in the building, lawsuits in the building, all because of a $25 trap. Some contractors say, I can't build your design because I don't have enough space to do that. Well, sorry, but you have to have. So you have to jack up the air handler, bigger sleepers on the air handler, or drill a hole in the floor, but you got to have the trap. It's not optional. Okay, air handler unit tops. We have rooftop air handler sections, package air handler, 4 to 36 tons, 14,000 CFM. Custom, 2.5 to 150 tons, 60,000 CFM. These are central station units. Built-up air handler, 37 to 750 tons, 300,000 CFM. That's a big air handler, by the way. Indoor air handlers, package unit, 4 to 36 tons. Custom, 2.5 to 150 tons. Indoor fan coil unit, horizontal concealed, 1 to 5 tons. Horizontal, 2 to 18 tons. Vertical, 1 to 3 tons. Computer room air handler units, which are vertical, 5 to 150 tons. And that's it for air handlers. That's everything you can get in an air handler, all the different types of air handlers. We didn't go into coil placement. We go into that in the system videos. So hopefully this was helpful. This will be the first one to get you started on air handlers. So appreciate you being here. Don't forget to subscribe if you haven't already. Have a great day, and I'll catch you on the next one.